Okay, position saya. So this topic is about bioelectronic devices. Uh, we propose some strategies actually how to develop flexible bioelectronic devices. So this is the outline of the talk. Number one is the introduction part. In here, we will be discussing about the um, we will be discussing about the challenge that we face to develop these flexible bioelectronic devices. And the second outline will be on the review. So review is something that is highly important before we start research. Secondly is to know how far we have gone so that we know it is at the pace of the direction. Outline number 3 is on the progress of my research group in this in developing the flexible bioelectronic devices. And at the end of the talk will be some remarks and future outlook on what we will be doing. Before I start to share with you in details, I believe everyone will be brief on the FYP2, project 2 for your final year project, in which that now you are in a constraint to conduct experiments. So interestingly, this time it will challenge you the ability to write. Number one, you have to review. Review means you read a lot of journals and you see some gap of knowledge or unexplored parts of the research. And then you write of what you have read, so it will be a review. So that's going to be a challenging part, but I believe everyone will cope with that particular approach. As for introduction, what is actually electronic devices, bioelectronic devices? Basically, they are devices that are flexible and friendly to be exposed or implanted to organism. So we also call these as biomaterials, but biomaterials not necessarily be electronic devices. So it could be anything. But in here we are covering both electronic devices that will be the biomaterial as well. There are many challenges that we face along the way to develop the flexible bioelectronic devices. This includes biocompatibility. It means that how the materials is behaving as non-toxic element to the body, to the human or any organism. Secondly is biostability. Biostability means how the materials will stay functional once we have implanted or put on our body. Number 3 is the facile fabrication methods. How the method is feasible, or what we call as how easy for us to prepare and fabricate the devices. Number 4, various range of electronic transition. We know that electronic devices are functional at different properties. For instance, different conductivity, different frequency or wavelength. So what is the best way to produce the materials? This, to encounter this, we first need to identify what are the properties that we want to produce or we want to achieve at the end of the fabrication. Let's say you want to produce materials with 10 cement per meter square. So how we fine tune the method so that we can achieve that particular range of conductivity. So there are a lot actually range. The range is wide, and we first need to identify, to be very specific of which area that we want it to be directed to. So some review, in 2015, during my PhD study, we published an article in a journal showing the synthesis and preparation of a conducting polymer in a form of thin film. We can see that the polymer is polyaniline. We name it as polyaniline. This is the blue color on top is non-conductive. After treated with acid, this polymer turns into green color. So this polymer, from the non-conductive state to conductive state, the changes are due to the presence of the acid here. So HX means acid, it could be any acid. As a visual assessment, we can see there are transition of color from blue from green. And we were wondering what are happening actually to these two samples. And further, we conduct a UV assessment. And from this analysis, you see that the dotted line is the blue one. And forget about the 24 hours. I'm showing you the right one actually. This is the real data. And the green one actually have got another bump here. This bump, if you see the first two bump, the first bump for these two sample, the dotted and full line, this is the dotted, this is the full line. They are having like a bump here. But for this one, for the full line, there is an additional bump here. This additional bump correspond to different chemical composition that are integrated into the sample, which it is representing the benzoate quinoid that is polarized due to the presence of the acid. I know this is quite, at some point this can be confusing, but what I'm showing to you is that on the non-conductive part, there are only two bumps here. Meanwhile, for the conductive one is 3 bumps. So the bumps are representing a different chemical structure to this polymer. Okay, this is non-conductive, which is a blue one. We call it emeraldine base. Once we introduce acid within the system, it becomes emeraldine salt. So this emeraldine salt, if you see, we can see the same figure. A or B are the similar one, but different type of acid. What it means by 0 hour? 0 hour is as it is. This one has been fabricated. Okay, 0 hour means it is in green state. Meanwhile, this is very acidic, yeah, and you see that this is reversible, yeah. So after putting this polymer into a pH of 7.4, this polymer turns into green color, and it is after 24 hours. You see the dotted line here, the dotted line here. It means that it is similar to the old of its version. It means that the conclusion from this observation, although you have A and B are different type of acid being used, although you have different types of acid, we see that, oh, this polymer is actually relatively unstable. We further actually have conducted XPS study, XPS X-ray photoelectron spectroscopy, to reveal the changes of the surface chemistry of the materials. And we see that there is a peak of sulfur. Sulfur comes from the acid. In here, we are using camphor sulfonic acid and para-toluene sulfonic acid. So we are using sulfur. But after we are exposing it to 7.4 pH, this peak disappears to a certain extent. So the full result and discussion can be found in this paper, which I have written it acceptable for publication in 2015. So it made us wonder, oh, then we need to find a suitable acid to make sure it sustains the functionality. It means it remain conductive after we are exposing to pH 7.4. What is important to have this specific pH? So in our body, in human body, we call it physiological condition, which temperature of 37 and pH of 7.4, which is relatively sort of normal pH. Means that if you want to insert or to what we call to introduce the biomaterials in the body, we have to ensure that the materials is biocompatible and remain functional once you want to include it in the body. And the next year, we published an article in 2016 in Science Advances together with my postdoctorate mentor, Dr. Damia. I was part of team. We have actually now in the past we have used camphor sulfonic acid and PTSA, para-toluene sulfonic acid. So we introduced and we tried another acid. We call it phytic acid. If you see this figure, yeah, this phytic acid has multivalent anion. Multi means it has more than 2. It means that it could be a minimum of 3 valent. So the multivalent anion is actually can work to bind to this structure. We have extended long structure of the polymer, and this phytic acid probably can enhance the stability of the material so that it will not the dopant inside the system, which is the acid, will remain stable to be in the system once we put at the pH of 7.4. What we did in the past is we produce and fabricate chitosan film. Chitosan originally from, it could be from prawn structure, but in the lab we just bought the powder and then we mix with certain acid and solution, so we produce the thin film. So what we did with the dry film after after we dried it for 2 weeks, we dropped the polymer that we have synthesized. So the emeradine salt with the presence of phytic acid. The use of phytic acid is with the intent to see that it will cross-link from the top and bottom of the structure. So it means that we want to lock the dopant to be at the incorporation of of a dry film of the chitosan. Maknanya on the top, this is the chitosan layer, and we grow the polymer. So we envision it as having bilayer films. Though after we manage to fabricate and we get the dry thin film, we see that we don't see a specific distinction of the 2 layers from the top and the bottom part. It means that it works as a 1 layer of film. So this is very interesting because I tried so hard to see if there is any distinctive area of the top and bottom layer, unfortunately, there is no specific area that we can observe. We want to see whether the phytic acid that we used is working well to be functional once we immerse and put in physiological condition, which is a human body temperature. Kejap saya ada kena call. Hello. Is turned on. You can hear my voice here. We continue. Sorry for the disruption just now. I've got a phone call. So in here, we want to see and measure whether this dopant has actually improved the system. And we have tried many acids before, and all are unstable. So in here, phytic acid was suspected and expected as well to work as a cross-linker with the polymer, which is the polyaniline, and the chitosan. So look at this figure, yeah. This is an XPS data. In my lecture for advanced materials characterization, I will explain it further for you. But to show you today is that we managed to see a huge improvement in terms of the stability of the polymer. You can see that this is the phosphorus. This is phosphorus. This is phosphorus. Phosphorus is the element that we wish to be there to have an extended functionality, because it works as a dopant to ensure that this materials is conductive. Okay, I have forgotten to tell you that the dopant is actually to ensure that this polymer is conductive. All right, so what we can see here, this phosphorus peak remain available after 14 days in phosphate buffer saline, which is this one, yeah. Physiological condition, we are using phosphate buffer saline. So this is a good news. To explain on the top part, I'll explain this in the class for advanced characterization using XPS. But things that you probably need to know here, the stability of the film increase, as we can see that these phosphorus peak are available though after 14 days. And interestingly, in this study that we have conducted, started in 2014 until it is acceptable for publication 2016, we have incorporated this this what we call this polymer, the plastic patch, onto the heart. So this is the heart of the mice that we have tried to see how this heart is compatible with our materials, and it is reported to be biocompatible. It behaves as biocompatible and non-toxic. So that was, I can consider it was a huge success in the past, but yeah, this is the thing that I am very happy with. So in here, the thin film works as bioelectronic devices. There are ongoing efforts to produce biomaterials as well as electronic devices so that it can work to help us improve the health in general. So in here, why do we need this patch? This patch is actually was pasted onto a hard tissue. At the hard tissue, there is a broken and healthy tissue. There are two parts. So what we did, we paste it with such parts of the patch using a laser. And then we see some interesting result in which that the broken part, which is the broken part of the heart, there are two parts, right? Broken and healthy. After we put the polymer at the two parts connected, the part of the broken tissue improve its rhythm after we electrically stimulate it. So this is like a fantastic observation, some promising result to show that this polymer, this plastic that is electrically conductive can improve the system of the heart, okay, especially on having the broken heart. Okay. Another review is that what I'm showing you some reviews in the past on please turn off your microphone. Who recently joined us? Hadi, Aisha, Sarah. Okay, I think everyone is putting the microphone off. Yeah. So if you see the next slide is about the review. And in here, we see that those are what I'm showing now is the efforts by scientists to produce the electronic devices. One of the consideration, if you see that this is the flexible, stretchable materials that works as bioelectronic, they are using different approach. For instance, if you see, A is engineering methodologies for intrinsic stretchability. They want to seek for some properties include the stretchability. So you're using this one, the liquid metals. Number two is the silver wire, in which that they are showing some hybrid nanostructure, in which that they are showing some function of the electric. It means that it works to a certain extent. C, you see some stretch part of it, in which they are using gold bell. Gold is definitely conductive, you know, gold should be conductive because it's highly expensive. And the fourth one is serpentine. This is an added pattern and designated parts of the polymer. And having said that this polymer was produced to have a conductivity properties, but the challenge will be on designing of the specific microstructure. So these specific microstructure are important to portray certain values of conductivity. And another substrate that can be produced in the form of kirigami. So those patterns or different shape and design are having all our effort to have a conductive parts of the devices. Okay. More importantly, they should have probably different properties. Like mainly they have to be biocompatible, electronically conductive, and also flexible. Another important part is we can see that the design strategies of circuit for flexible bioelectronics. And you see this one, circuit of the liquid, conductive gold electrode with wave application. I think it was actually, oops, cross. Okay. So those are the things that are important for us to consider. Ni terbalik ni, dia punya caption. I pun tak perasan. Okay. So in having bioelectronic devices, they are listed here some possible flexible biosensor in detecting a few consideration. Number one, the physical signal biosensor includes microforce, pulse, voice, breath, temperature, organs, and brainwave. Semua ini adalah untuk memberi signal kepada sebarang changes. So any changes will lead to something. Okay. Number two is biochemical signal of biosensor. It means that you are producing bioelectronic devices that can be a sensor to this one: blood, sweat, tears, saliva, gastric fluids. Okay. It's important to develop this because the disease sometimes are very complex and unpredictable. So those devices are designed to help in sense any irregular mechanism takes place. Okay. Number four is wearable biosensors on body or integrated into accessories. It could be anything. The easiest example for you to understand this is you are putting a smartwatch kan. Some of you, saya tak pakai pula kat rumah kan. This smartwatch is very lightweight and mini, so it is developed from certain part of the electronic devices. Can you imagine in the future you just wear like a normal shirt with certain properties of sensor? So I think there are some developed and developing still. So yeah, those are the things. On top of it, on top of everything, back to the objective, we want to produce something that is beneficial and crucial for people. Okay. Implantable biosensor. It's very clear stated here, number 3, biosensor that is implantable to human body. So first thing first, it should be biocompatible. Number 2, it should be functional to certain designated time frame that you want it to be functional. Okay. Number 3, how feasible is the process? Okay. In our group, some progresses have been conducted in my team with the team. So what we did was we synthesized. This is like a continuity of my PhD work, but I focus on the fabrics because fabrics are flexible. So we synthesized the polyaniline, in which it can work as a non-conductive or conductive. Green is the conductive one, non-conductive one is the blue. So the state of the color representing the chemical state. Okay. For instance, for the green powder, it has a protonated state. Protonated state means that it has acid or dopant incorporated into the system to make it conductive and functional. And following fabrication and synthesis of the polyaniline, this polymer can be doped. This polymer can be introduced on fabrics, different fabrics. And you see that we have, I think this one is jersey type fabrics. The blue one is after we immerse in the blue color of the polyaniline. So this is in a powder form, and we introduce a solvent to make it as a liquid. And then we immerse this empty what I mean is the bare fabrics onto the solution. It becomes blue and green respective to the solution that we produce. And we have venturing about 5 types of acid in here. That's why we know if it is blue, it is conductive and relatively non-conductive to a certain extent, and green definitely are conductive. So the method to produce this is the thing we use aniline. Nama dia tadi ialah polyaniline, yeah. If you see polyaniline, basic polymerization, it should be from aniline, and this is the monomer become polyaniline, which is the polymer. So we use ammonium persulfate, works as the oxidizing agent. We mix with aniline. And then this is the filter. After we mix, we get this like a black and green color. And after we'll do some filtration, we get the polyaniline amiridine base powder. Then we introduce acid to make it green. And then we do the immersion of the fabrics onto the solution. And we finally get what we have here. These are the colors. These are the colored fabric which we introduce polyaniline within the system. All right, my master student Zatul work on polyaniline fabrics doped with para-toluene sulfonic acid, and these are the changes. As you increase the concentration, the conductivity also increase. We do some Fourier transform infrared analysis, and these are the spectra to show there are some changes as the effect of different doping system, which is different acid, and some control, which is this is the bare fabric, and this is the undoped one without having the acid in the system. Interesting part of it, we see some morphological structure of the doped and undoped fabrics. In my views, I see that there are not much changes on the structure. So it made me think that the polymer itself is actually well embedded into the structure of the fabrics. More or less, they look the same. So these are the different from the bare, undoped, and doped fabrics. If you see, we also did some analysis on the ability of these fabrics to be an anti-infection agent. And if you see what we have seen here, this is doped fabric, doped with the acid. Initially, it is green, and it becomes this color. And this is undoped fabric, and this is the control. This is at the bacteria plate, yeah? Now we can observe that there is an inhibition zone formed at the outer layer of this specific sample. Amazingly, this has come out to another perspective, and we conclude that these fabrics can work as anti-infection fabric. In other words, we say that antibacterial fabrics. We are very happy with this paper, but yeah, further investigation need to be conducted before we can apply to human. Next, Zaltul also ventured on the different fabrics. Just now is the jersey fabric, yeah. So this one is polyester fabrics. We did some measurement. This time we are using sulfonic acid. So different type of acid. Just now, I think we are using what acid is it? Para-toluene sulfonic acid. We try another acid. Yeah, we see not much different, but some of the similar morphological, and it was also published in a journal. More or less, we tried so many types of acid. Yeah. And Zatul actually conducted another project. This is a bigger project. Zatul produced, we are using phytic acid, the acid that I have been using during my PhD work in the past for the patch. And well, you see there are some interesting results over here. As expected, if you increase the concentration of the dopant, the conductivity increases in line with the percent of dopant within the system. We explored two types of cotton and polyester, red and green. Green pula. Red and black. Black is cotton, polyester is red. We see that the polyester fabrics, this is the jersey type, compared to this is cotton, shows an increasing of conductivity much than the cotton. And we conclude that, probably this is because of the good incorporation in which that the polymer insert well into the internal structure of the polyester fabrics, which is the jersey type. If you see this one as well, they are here, you see doped penny fabrics. This one is undoped. Undoped is the C one. B is the cotton fabrics. A is the undoped one. We suspect that with the increase of the acid within a system, because it's kind of overloaded, you know, when the acid amount that we have included within the fabrics is immersed well, but to a certain extent, if extra loaded, it will be what you call that, some residue on top of the surface. So this is what we see. Same goes to the cotton. Okay. Antibacterial assessment, this is a normal one for FTIR spectra. I think you know about this, but the reason of conducting this FTIR spectra analysis is because we want to see any chemical structure changes, because we are using two different types of fabrics. Antibacterial assessment. This one, you might not be able to see it at the greatest magnification, but we are showing now some sort of inhibition zone that the polymer produce as we expose it to the bacteria. Okay. Polyaniline doped phosphoric acid is conducted by Nazrin. This is the cotton fabrics. Cotton fabrics is an interesting part of the research, in which this is the UV analysis. What I'm saying here, there is an additional bump for the green part of the polymer, which I have explained in the previous slide, showing that this polaron works to show that the acid has already been included to give some significant amount of conductivity, right? There are some conductivity, as usual, if we increase, it will be increased. And this, we can see again, that by using another type of acid, which is phosphoric acid, because we tried so much to see if there is any variation of having different type of acid in terms of conductivity. We have collected much on the details of the conductivity data. We see some range. Okay, so the reason we do this, because we want to see that, for instance, this application needs certain values of conductivity, then we hit for that. We can go here and there, depends on the acid that we are using. Okay. Another paper, this is an preparation, is very nicely captured by Nazrin. We are using polyester fabrics, yeah, more or less about the same stories, but different outcome in terms of conductivity values. Interesting part about it, as I said earlier, we are trying to develop a library that can suit for any specific application. So in the future, if you come to me, okay, doctor, I would like to have a conductive fabric, so flexible with the amount of conductivities, blah, 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 blah. Okay, see, okay, you can use this formula. Okay, that was the reason why we have sort of like range of type of acid incorporated into the fabrics. Faiz actually has published a journal which is accepted early this year. So this is his final year project that we can see some interesting finding. Similar patterns and similar story, but different type of acid in here. So he's using hydrochloric acid. As expected, the amount of the dopant plays a big role to ensure that the conductivity values increase. Some interesting part is that the polyester again showing a significant amount of conductivity compared to cotton. We suggest that this observation are in line with the previous findings to show that this polymer, the polyaniline, is inserted well into the fabrics compared to cotton. So means that polyester is much better than cotton for conductivity purposes. Okay, some measurement on the conductivity, different approach, but this data can be read as this one. This is actually the raw data and then converted into this graph. Before I touch about the thermal analysis of this one, if you see this, this is the scanning electron microscope images that we have captured captured for A is the bare cotton, B is the bare polyester fabrics, C is the dope cotton, D is the polyester fabrics. Awak nampak tak? This is very nicely portrayed and captured compared to this one. This is the cotton. It means that the acid, the polymer is actually not embedded well in cotton. Meanwhile, for polyester fabrics, it worked very well, fantastically. Okay, this is very nice piece of work. And if you see, I think you have learned this one as well in the class about the thermal analysis. So we've been using thermal gravitational analysis, TGA. Kejap ya, ada saya kena macam-macam. Yeah. It's okay. Okay, if you want to see the changes of the type of the polymer, we see that okay, the black line, bare cotton. So the decomposition takes place after this temperature. Okay, if you see cotton fabrics, the black one is the bare cotton, and the red one is actually showing that the decomposition will be about at the same temperature, but will be much earlier, okay, compared to the blue one. So it decomposed at this rate, yeah. For polyester fabrics, bare, this is the control, bare without having any polymer. This is the graph. Obviously, we see that it is decomposed earlier than the bare cotton. Interesting part about it is it has shifted. This line shifted. It means that its thermal character has improved a lot, in which that it is not easily decomposed after we introduce polyaniline into the system. This is a piece of amazing work. Okay, I truly happy to see this one. Okay. All right. So moving on, morphological structure and structural and electrochemical studies of conductive polyaniline coated polyester fabrics. Again, this is the synthesis process, and we see some morphological changes. Again, the same one, and this is what we call that. This is another different type of acid, which is the PTAC acid. Okay, and we see some changes if we increase the dopant percentage. And this is another piece of work. Oh, kita sekedar sejam eh. Okay, I need to finish this one soon. This is another work by Faiz. Please read on the thermal studies of the PTAC using DAC and TGA, and we will discuss this after. And there are some progress. They are trying another conductive polymer, which is P.PSS. We tried to produce one. These are the progress we managed to produce, and we're thinking to include it into the fabrics. This is the FTL result, and some future remarks and future outlook. Fabrication and the biostability, sorry, there is a typo. Efforts are still ongoing and remain challenging. Strategically, it requires a focus on the real desired properties and requirements scale down the objective towards tackling specific problem. So we were thinking to produce more film, maybe this time with the pattern part. Okay. Right, this is my research team, and thank you for them for being able to synergize synergize the work together with me. All right, thank you very much for this, and to stop sharing.